Good morning, friends. I am here again for my last lecture for the aircraft stability and control. In this, I am going to cover about lateral directional motion and its modes. This is a just introductory class. This is the last lecture, but I will also be covering some numericals. I will have 10 tutorials, and also next 10 I will be taking some questions and some definition and terminology and question answers related to aircraft stability and control. So as per the book I am going to complete today, but further development of the previous classes, their clarifications, and also few of the applications, experimental analysis, and other things I will be covering in my tutorials as well as in my next session, which will be the definition and terminology. In that I will be taking the few important questions and I will be discussing. Okay, so in this class I am going to cover lateral directional linearized equation of motion in Laplace form, 3 degree of freedom analysis of the lateral directional modes of the motion. I will also discuss Dutch roll and spiral modes. In this lecture, I am going to answer few of the questions like this. What is lateral and directional equation of motion? Then different dynamic modes in lateral directional conditions. So just I will give a little brief of all the previous units. In my module 1, I have discussed about the longitudinal static stability. In that, we have seen that in the longitudinal case, suppose this is the aircraft is flying, we are concerned with the pitching motion, if nose up and nose down. So if the aerodynamic center is behind the center of gravity, the aircraft will have nose down tendency. If the aircraft has the nose down tendency, it means Cm alpha, dCm by d alpha is negative. And the second condition is Cm naught should be positive. So if we see here that if I draw the plot of Cm versus alpha, plot should go like this. This is the Cm naught and this is the dCm by d alpha is less than 0. And Cm naught should be greater than 0 or positive. Here it should be positive and it should be negative. So we have covered this longitudinal case, and for the second module we have seen that the coefficient of yawing moment and coefficient of the rolling moment, this is called the Cn and Cl. This is the rolling moment coefficient, and this is the yawing moment coefficient. Okay, so these two parameters are very important to understand about this yawing and the other lateral and directional stability. So we can see that if this is the plot beta versus Cn, beta versus Cl. So the plot for this is called Cn beta should be greater than 0. But for this Cl beta should be less than 0 or negative. and this would be positive. So these are the two conditions. If we are able to meet this condition, we can say that aircraft is stable, statically stable in directional, and this is the about rolling. So this we have already covered. Now these are the equations, these equations we have already derived in our previous classes. I am just repeating here to understand that what equations we have derived. These are the perturbed equations of motion in lateral and directional. In lateral and directional, we have one force and two moment. The force is in the sidewise in y direction. If it is moving in this way, so this side is y and this side is z and this side is x. So in this, only one force means a side force will act in the sidewise direction, and two moment, that is the rolling moment. If this is the thing, this is the rolling moment, this is the rolling moment, and this is the yawing moment. In this we have these three motions. We can see here that this v dot, this all things already I covered. Beta is our side slip angle, y is side force with variation of beta, beta is side slip angle. Okay, here p dot and r dot, so here rolling and the pitching, here delta r here and delta a. So here delta r is a deflection of rudder, and here this is the deflection of aileron. Okay, so here T is a thrust force, and T, it is the moment due to the thrust, NR moment due to the rudder deflection, and delta A moment, yawing moment due to deflection of aileron. Here we have to understand that lateral and directional are coupled with each other. However, longitudinal motion is not coupled with like lateral and directional. It means once you roll the aircraft, yawing will be there. If you yaw, roll will be there. And in this way, one more term, it is called the adverse yaw, is also happening. When you try to roll the aircraft, one side lift will be more and another side lift will be less. The side which is producing more lift will also produce the more drag. So if you are rolling like this, nose will go towards the left. That is called the adverse yaw. Here in these equations, we can see that there are 5 variables, that is the velocity v, p, r, phi and b. This you can see here, it is primary. Here these are the theta and phi and beta. These are the 5 variables, and 2 functions are forcing functions. These we have to apply. Delta A is a elevator deflection, aileron deflection, and delta R is rudder deflection. Okay, hope all the parameters are here cleared. Here A1 we have put here, A1 means IXZ by IXX, and B1 is equal to IXZ by IZZ. So wherever you see A1, B1, they are in fact IXZ, they are the inertia. It is a ratio of 2 types of inertia. Now we can see that with 5 variables and 3 equations, it is not possible to solve. So we need to take kinematic equations and the assumptions of a small pitch attitude angle theta1 for wing level roll angle phi is equal to 0. With these assumptions, we can find that this P is equal to phi dot and R is equal to psi dot. Also for the small perturbation, beta is equal to V by U1. So V is equal to beta into u1 and v dot is equal to beta dot u1. These are the rates. So therefore, we can reduce our aircraft motion variables to only 3, 1, 2 and 3. These 3 are unknown. With 3 equations, we can find out these things very easily. So here we have to use the Laplace transform for solving this equation which I have shown here. Here we have made all the functions with s here, and this you can see here that everywhere we have added the s here, beta s, phi s, delta as, delta rs in all the 3 equations. So we have got here that combining terms and moving the control inputs to the right hand side of the equal sign, we have here, this you can see here, these are the y delta a delta as plus y delta r delta r. These all are the control inputs. You see, delta a is control, delta r is control. All the controls we have made to the right side, and non-control items we have made in the left side. And so we got these equations. Now regrouping these things, we got here su1 minus y beta minus syp plus g cos theta 1, su1 minus here beta s, phi s and psi s. Here all the 3 angles are there, and here if you see y delta a, y delta r, l delta a, l delta r, n, this y is a force, l is a rolling moment and n is a yawing moment. And this will happen due to the deflection of ailerons and the rudders. So here, and each of the 6 lateral directional transfer functions can be determined using the Cramer's rule. The 6 lateral directional transfer functions are beta s divided by delta as, beta s divided by delta rs, phi s divided by delta ar, phi s divided by delta rs. Means this beta s delta a delta r, then phi delta a and delta r, and the psi delta a and delta r. Means all these 3 variables are taking place when we apply the aileron and the rudder. So there are 6 lateral and directional transfer functions versus the 3 longitudinal motion. We have 2 possible control inputs. These are the delta a and delta r, each of which can cause changes in the 3 lateral directional motion variables. Each of the lateral directional transfer functions can then be represented as the ratio of 2 polynomials in Laplace variables. This you can see here that beta, phi and psi, beta s by delta s, phi s by delta s and psi s by delta s. We can see here that all the in equation 3, 4 and 5 represents the general form of the 6 lateral directional transfer function. The numerator of each lateral directional transfer function is different. If you see, the numerator is different but denominator is same. In all the 3 equations, all the denominators are same but numerators are different because the numerator affects the magnitude of the response. So this numerator is the important parameter which affect the aircraft response. Each of the 3 motion variables will have different magnitude of the response. So each of the 3 motion variables, these are the beta, phi and psi, they will create a different magnitude of the response. All will not be the same response. Here we can see that all 6 lateral directional transfer function have essentially the same denominator which leads to the same characteristic equation. So all are having the same denominator, that is e s to the power 4 f s to the power 3 g s square plus h s plus I is equal to 0. The extra s in the denominator of the phi s delta s transfer function indicates that the airplane is neutrally stable in heading. Here we can see that 3 degree of freedom analysis of the lateral directional modes of motion. The 3 lateral directional motion variables, they are the beta, phi and psi, leads to a 3 degree of freedom solution for lateral directional motion. Normally, the 4th order characteristic equation for lateral directional motion is written as the product of 1 second order, that is called ordinary and oscillatory, and 2 first order, that is called non-oscillatory polynomials. So in this you can see that we have here, this one is the second order, and here we have 2 equations. These are the first order, this is also the first order, and this first order are non-oscillatory, okay, but this is the oscillatory, okay. So in this what will happen? In this you will see that if this is the motion, it will go like this, like this, like this, like this. But in this what will happen? Non-oscillatory. If you disturb once from here, it will reach like this. It will not go beyond. It will not oscillate. So like this motions will be there. So here you can see that here s square plus 2 zeta dr omega and dr s plus omega square and dr, here s plus 1 by tau r, s plus 1 by tau s is equal to 0. Here you can see dr. Dr means Dutch roll. So here Dutch roll will be there, and this Dutch roll is an oscillatory motion. However, s is a spiral mode and r is equal to roll mode. This spiral mode and the roll modes, they are not oscillatory. That we have to understand, that in the lateral and directional modes, Dutch roll is oscillatory, but spiral mode and the roll modes are not oscillatory. The coefficient of each characteristic equation change with flight condition, airplane mass, mass distribution, airplane geometry and aerodynamic characteristics. So here, what is the Dutch roll? Dutch roll is very important and very, if it is not good, it can cause a very serious problem also. So the Dutch roll mode is a second order response, complex conjugate roots, characterized by concurrent oscillation in the 3 lateral direction variables. These are beta, phi and psi. Beta is side slip angle, phi is roll angle, and the psi is yaw angle. It was observed that side slip generates both yawing and rolling moment that leads to a coupled motion between beta, phi and psi. These oscillations may be of high or low frequency and may be lightly or heavily damped. The Dutch roll usually begins with a side slip perturbation followed by oscillations in roll and yaw. So what is the Dutch roll? The Dutch roll begins with a side slip perturbation. First side slip perturbation will follow, and then oscillations, aircraft will start oscillating in roll and yaw, means like this and like this. Okay, so if it is like this, aircraft is moving like this, so it will oscillate like this, like this. Okay, so at a time oscillation and oscillation in yaw and oscillation in roll, all the 2 things will combined in Dutch roll. The Dutch roll motion is sometimes like that of an ice skater body weaving back and forth as weight shift from one foot to the another foot. As the magnitude of CL beta is what? It is a coefficient of rolling moment, becomes larger. More roll coupling is present during roll oscillation, Dutch roll oscillation, and the Dutch roll characteristics typically become more objectionable. Dutch roll characteristics adversely affect precision tasks like air-to-air and air-to-ground tracking and formation flight. So Dutch roll is affecting the precision task like bombing, missile firing, air-to-air tracking, and also it is affecting, if it is you are about to land the aircraft, it may affect very seriously. So during this type of precision task, if your aircraft is doing the Dutch roll, it is not advisable. It is not very serious, accident may not happen, but the precision task could not be performed. Here I have illustrated the Dutch roll. What is the Dutch roll? We can see here the first diagram that the aircraft is here. In this case, aircraft is flying straight and the level. All of a sudden, some phi angle, this is the roll angle phi, is taken place. Due to this roll angle, a side force will be generated towards this and aircraft will reach here. It's supposed to go in this line, but aircraft has moved in the one direction. It will move in the direction in which the wing is upward. And then when it is moving upward, next oscillation, it will go to the right. And again left, again right, and after some time, it will come to the original position. So it is, if you are viewing from the front, you will see like this. But if you see from the top view, just you can see here, initially your aircraft is here in this line. Due to the aircraft wing roll in one direction, aircraft has started yawing in this direction, again in this direction, again in this direction, and after some time it will reach to the original straight line. The same if you see from the front, I have shown here. This is also the front. So aircraft is here. It's supposed to go like this, but it is going like this, again going like this, going like it. It means it is oscillating like this, like this, like this. So this is called the Dutch roll, and this is not good to have Dutch roll for the betterment or for the precision of the flight. You can see another diagram here. If you see here that aircraft is here in this position, it is going here, again it is going here, it is going, and like this, slowly the amplitude is coming down. You see here, it is, if you make from here a center line, like this, you will see that here amplitude is very high, little low, lower, and slowly it is come to the same line. So aircraft is stable here. So mostly the Dutch roll is the stable aircraft. It will not disturb the aircraft dynamic stability. So it is a stable aircraft, but it needs some time and it gives some disturbances so that aircraft will not create the problems. Now another mode is a roll mode. So the roll mode has a real root. In this you have the real root. We have seen that we have the one quadratic equation and two equations are the non-quadratic equation. This you can see here. So in this, the first order, these equations are the first order. So S plus 1 by tau R. This is the first order for the roll, and we are going to discuss in this. So the roll mode has a real root and a first order non-oscillatory response that involves almost a pure rolling motion. Roll means pure rolling. Means if it is you are rolling the aircraft like this, no yawing will not be there. Okay, like this. Okay, so it is stable at low and moderate angle of attack, but may be unstable at high angle of attack. So it is depend upon the angle of attack alpha. If the angle of attack alpha is less, it will be stable, and if angle of attack is higher than the some limited value which is given by the designer or manufacturer of the aircraft, it can be unstable. The roll is excited by aileron input. So how the roll is given? We have to use the ailerons. Ailerons are on the wing. So if you move wing up, that side aileron will go down, and the wing which is going down, aileron will be up. So you have to excite the aileron. If a step aileron input delta A is made to the aircraft, there is an exponential rise in roll rate 5 until a steady state roll is achieved. The time taken during the exponential rise to the steady state is interpreted as the finite delay, which we usually characterize with the time constant tau r. So how much time it is taking? You apply the aileron, aircraft will roll. After rolling, how much time it is taking to stabilize? Otherwise, it will be like this, like this. So try to, after when you apply the aileron, how much time it is taking? It is a finite, few seconds it may take. So that time is called the time constant. If this time constant tau r is too large, time is very much, the aircraft is considered the sluggish because it takes too long for the commanded roll rate to build up. So suppose pilot has applied the aileron, and after application of the aileron, it is taking more time. It means that whenever he is applying the aileron like this, after few seconds, 10 seconds, 20 seconds, it is reacting. Then pilot will say that your ailerons are sluggish. Okay. Likewise, if this time is too small, 1 seconds or 0.1 seconds, the aircraft may be too responsive. Okay, so if it is like this, he is applied like this immediately. So it is called too responsive. So it should not be too responsive, it should not be sluggish. In between, your tau r should be there. Means that time which is taking to stabilize the aircraft in rolling should be within the limit. It should not be too small and it should not be too sluggish or too more, so that aircraft can reach in given time for the roll condition as pilot want. The aircraft may be too responsible to external disturbances such as turbulence. So what will happen? If aircraft is flying like this, okay, you can see, if aircraft is flying like this and pilot is rolled and it is vibrating like this, if any gust has come and it starts shaking like this, it is not good. So if it is passenger aircraft, passenger will feel very, very discomfort whenever rain or anything, any disturbances is occurring or any turbulence is happening. It should not vibrate like this. It should take slow and it should, within a given time, it should behave. Now the third and the last mode is spiral mode. The spiral mode is a first order response, that is a real route, slow roll and yawing motion. In the roll, only the roll will be there. But in the spiral mode, you have the roll plus yawing. Okay, just like aircraft is flying like this, you give the roll, yawing will be also there. Roll and yaw, both are there. Then it is called the spiral. It may be stable or unstable. So this spiral may be stable or it may be unstable. The spiral is initiated by a displacement in roll angle. Means if you take this aircraft and you roll it, it appears as a descending turns with increasing roll angle of unstable. Okay, so the spiral is initiated by a displacement in roll angle and appears as a descending. So it will appears like this. Descend. Aircraft will try to descend and started turning also. You have given only the roll, but due to this roll, it is trying to yaw as well as increasing this phi or the roll angle. If the spiral is stable, the aircraft returns to the wing level after a roll angle displacement. So if your aircraft is stable, after this action, it will again come and it will start moving in the same condition. The primary motion variable during the spiral mode are phi and psi. So what is the phi? It is a roll angle, and psi is the EI angle. With beta means side slip angle will remains 0 and it may be constant. Okay, high degree of lateral stability, that is CL beta, is called the lateral stability, will tend to make the spiral stable. If CL beta is high, aircraft will be stable. With a high degree of directional stability, CN beta will tend to make the spiral instability. If the CN beta is more, then aircraft will be unstable. And if CL beta means lateral stability is high, aircraft will be stable in spiral mode. And if the high degree of directional stability, CN beta, will be there, then aircraft will be unstable in spiral mode. Spiral instability can be tolerated as long as the aircraft's double its gradual greater than approximately 4 seconds. So, spiral instability can be tolerated as long as the time to double the gradual this oscillation is more than 4 seconds, then aircraft will be stable. Here I am showing you a very nice characteristics of spiral mode. First diagram, figure 1, which is a spiral mode of the airplane. In this you can see that as and when this is the side slip angle, you have given the wind aircraft is moving in this direction, and here you have given the phi angle. This phi angle will try to make the aircraft fin a side force. This side force will try to make the aircraft in this wind velocity will be in this direction. Your phi will increase here. Beta is almost constant, but you can see here as the beta is here, it start yawing, in this steady increased yaw is increased. However, if you see here, this phi is increased, here is less, more, and it is the highest. The rolling is highest in this third case. So it is a spiral modes. You can see in this diagram, it is graveyard spiral, highly unstable. If your aircraft is very highly unstable, lot of chances of aircraft accidents are there, and so many aircrafts have crashed due to this spiral modes, highly unstable conditions. This you can see here that aircraft is here and you gave the roll. By giving the roll motion, aircraft started yawing, and if it is increased much, the roll will be very high and you cannot control the aircraft, and here aircraft will be crashed. In the second case, you are flying the aircraft, you gave a little roll, pilot is able to control, you come here, again here roll has happened, but the roll angle has increased from the required condition, and aircraft has again reached to the graveyard and a crash will happen. So spiral modes are very dangerous. Pilot tries to control this spiral mode so that aircraft is safe in flying. So friends, I have covered all the topics related to the aircraft stability and control. Hope you have enjoyed my classes. Try to listen as and when possible. And in my next classes, the classes will be the tutorial. In that, I will be covering some basic topics along with some numericals. So 10 classes will be the tutorial, and next 10 classes will be the question answer explanations from the previous questions and some other gate questions I will be explaining. So please be tuned and listen my next tutorial class starting lecture number 41 to 50. Thank you very much for joining my class. These are the references which I have taken from Yachout, most of the topic, and then Nelson. Thank you very much. And here I am ending this lectures series of this. However, it is not the end of this aircraft stability and control. We will be solving some numericals, some new topics in this, and as a discussion issues I will take in the next classes. Thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.